Hello and welcome back to Source Dive, where we take an in-depth look at some of the most interesting low-level open source code bases out there and really try to get an understanding of what makes them tick. So we're currently looking at XV6, and in today's video we're going to take a dive into the kernel physical memory, physical page allocation memory mechanism. Now this is one of the kind of core fundamental aspects of the operating system where we actually take the physical RAM that we have, that the kernel has to keep track of. Kernel is the one who's managing which user process is going to get which slice of RAM, and this mechanism is used to basically distribute memory for internally in the kernel itself and also any user space things that are required for it. It's pretty interesting. It's going to take us into some areas that cover things like virtual memory, although we'll talk about that in more depth in a later episode. And I think you're going to be kind of surprised and intrigued by some of the mechanisms that we find in here. At least I certainly was when I started looking into this. It was a pleasant surprise and an impressive algorithm. So, I mean, that's kind of what you find all over these kind of interesting code bases, is surprising things that you never would have thought of yourself. So it's a great way to learn. All right, let's get into it. Let's have a look. So what we've covered so far, in fact, is everything that goes up to here, kind of initializing the entire operating system from kind of bootstrapping perspective, getting from ourselves from the lowest level assembly instruction that begins the machine, to setting up a stack, to arriving in the first layer of C code where we can actually sort of like kind of arrange the system and get ourselves into kind of ready for the operating system. Then we're into the operating system and we prefer get everything we need to actually print stuff to the screen up and running as soon as possible so that we can actually kind of debug the system and get some useful information out of it. That brings us to this kinit function, which is labeled as the physical page allocator. So let's take a little walk into this. So this is actually quite a small file. There's 83 lines of code in this file. And the comment up top says physical memory allocator for user processes, kernel stacks, page tables, page table pages rather, and pipe buffers. Allocates whole 4096 byte pages. So that's what it does. We don't have to understand what all of that means right now, although hopefully by the end of this we'll understand at least the most important parts of it. Okay, so we bring in some header files that are stacked around. We'll go into some of these. We declare some functions up top so that when they actually get called before they're defined, that's possible. That's just something you need to do in C. Like if you use a symbol before it has actually been kind of defined within the file, you kind of need to kind of declare it up top somewhere, a forward declaration of that. Next we have an extern car end array, which is actually labeled here as the first address after the kernel defined in kernel.ld. We looked at kernel.ld in one of the first episodes, but it's a good time to come back and look at it now. This is the linker script. So this is what actually tells at the final step of compilation, when we've compiled all the individual translation units, all the individual C files and assembly files in the system, we have to link them all together. This is the final step, and this linker script is kind of provides a guide of how we do that. It's a kind of a set of restrictions that we have to have from our final output program, like for instance that everything will begin kind of reference to this address, which is the beginning of RAM, because of course we're going to load this program into RAM. So if we talk about there being a certain, like we're jumping to a certain address, it's all going to be sort of calculated relative to this very first address. Then we have the various sections. So this is the text section, it's code. We have the read-only data. Then we have the data that has been initialized. Then we have the data that has not been initialized. And then what you can see is that there is this statement at the end that says provide end.equals dot. And in kind of linker script lingo, what this actually means is the dot is always tracking where you are right now within sort of like providing relative addresses. So like up here you can see that we set the dot to 8 million, 80 million hexadecimal. And then kind of as we stuff different sections of code into things, of course, like we need to increment that address. So by the time we get down to this point, that address is kind of, it has been incremented a whole bunch. Wherever that lands, wherever that happens to be at the very end of this, we mark it as the end, and we provide that as a symbol. So this end, coming back to kalloc, when we see here this extern car end, this is actually referring to this symbol given by the linker script. So it's not a symbol that actually exists in the code, it's a symbol that's kind of injected during the process of linking. And kind of the way it's set out here, declared as an array, is just a convenience to make sure that when we actually access it, it behaves like an address. That's the short way of putting it. If you experiment around with linker scripts and kind of providing symbols, you'll see that the symbol is provided, but you have to kind of take its address to get the value you're after. Like what we want to know is where is this? What is the end? What is the last address of the kernel? And by kind of putting these array brackets, kind of saying that this thing is an array, this is a very simple way for us to do that. Okay, so this is just getting that out of the way. We now know where the very end of the kernel is. And keep in mind here, that's tracking all the code of the kernel, but also after compilation, where all of the variables are going to go, where all of the read-only data is going to land, and like where anything else like that. So basically everything as we know it when we compile the program gets us to a certain point. Everything after that is kind of free memory, right? It's everything from the end of that kernel until the end of physical RAM. That's what we've got to play with at that point. Next, there is a definition of a structure. It's called run, and it's a weird little structure. It's a structure that basically contains one member. So it's got like kind of, if you're coming from a high level language, kind of like an object with one member inside. And that member is a pointer to another structure of the same type. So, and you'll notice it's called next. This is basically the most minimal linked list implementation you can imagine. It's like a linked list that doesn't even contain data. It's just purely one thing pointing to another thing, pointing to another thing. It's kind of a bit of a weird concept. You have to wrap your mind around it a little bit. We'll see how it gets used. Next, of course, we've got kind of like a little piece of data that wraps up all of the interesting things that we have in this module. So it's called kmem, and it keeps track of a spin lock. Of course, we've seen spin locks now. They are used throughout the operating system to make sure that we have mutual exclusion on resources. Basically, we can use this to make sure that any multiple CPUs in the system which are going to try and access, say, the page allocator, they're going to have to take it in turns, right? They're not going to be able to come and all try and do the same thing at the same time. They're going to be forced to take turns to do this. That's what spin locks are all about. There's a whole episode on spin locks if you want to get a bit more into it, but for now, we can just use them as a tool, right? They're a tool for mutual exclusion. And next we have a pointer to one of these structures called the free list. So now here what we have is space for a pointer, so not actually a structure in this thing, a pointer to one of these structures. And that structure, of course, then if we kind of read through whatever we had, if there was a value in here, we would have some access to some next piece of memory. Next structure, rather. This will become clearer. If this isn't clear to you right now, that's fine. Like this will become clear. All right, and then finally, here we have the kinit function. So this is what we're actually running here. So kinit, what do? We initialize the lock, standard stuff. We've seen that. Then we call this function free range, and if we look down here below, right? Free range is a function that doesn't return any items. It's void, and it takes in two parameters. it takes in a pointer to PA start. That's a physical address start. That's the start, the physical start address that we want to free. And then there is a pointer to a PA end, a physical address end. Now notice what we pass in here. These are both void pointers, right? And a void pointer is just, it doesn't actually point to any particular kind of data. It is just a sort of free floating address. And this is C's kind of most low-level generic type there is, actually, the void pointer. It's basically a way of, like, if you want to use a void pointer, you always have to cast it to something. So you actually have to say what the data is this thing points to. But this is often used in the case that, like, that data that you're referring to is actually not as important as the fact that you have just an address to something. So that's why we're using a void pointer here. And you can see that what gets passed in here is the end. So that's where we start, the end of the kernel, like after all of the kernel stuff. And where we end here, the PA end is confusing because PA start is end here, but PA end is this define here, phi stop, which is presumably physical stop, the physical end of memory. So let's go to that define here. That brings us into memlayout.h, which we've actually seen before a couple of times now. So down here we have this whole calculation for where the physical stop. Sorry, I'm saying physical stop, and I think it's physical top, like the top of physical memory. This is why naming is actually important, and try to not be so ambiguous. But basically what this define is giving us is like the sort of the very end of RAM. Like, okay, we've got this much RAM, that's it. 128 megabytes in the default case of XV6. 128 megabytes, that's the end of RAM. So the way this is computed is we know where the kernel starts. That's this address 80 million. That's already been kind of explained. So the end is, well, that kernel base plus 128 multiplied by 1024. That's going to give us 128 kilobytes. And then once again, multiply that by 1024. That's going to give us 128 megabytes. So the physical top of memory of RAM is the kernel's beginning plus 128 megabytes. That should make some sense. It's basically just it starts here and then we have 128 megabytes of memory. So wherever that ends up, that's the end of memory. So what this statement is telling us is that we're going to try to free a range of memory that starts here at the end of kind of wherever the kernel finishes up, that point, all the way to the end of memory. So what are we doing here? We're going to be preparing all the free memory that we have. That's what we're doing. That's the idea. So free range, what does this function do? What this function does is it calls, well, we start out with a character pointer. So that's just something that's pointing somewhere. It's kind of a free variable that gets used in the loop so that we don't have to do anything weird with other variables. So we've got this character pointer and we assign it to the physical address start cast to a uint64. So this is a void pointer now. We're casting it to a uint64. Gives us the address as just a regular integer, basically. And then we're using this macro pg roundup. So let's go to that because that's going to be important for us to understand. So pg roundup size. It's a complicated looking piece of code, and I've actually explained a piece of code like this exactly. I walked through the whole macro in the bare metal programming series that I've done. I'm not expecting that you go off and watch that whole series to understand this, but basically what this does is this rounds up to a certain size. So let's imagine to this, like we passed in pg roundup 45. Let's say that's the number we passed into this. the outcome of this is going to be 4096 because we're rounding up to the page size. That's the idea here. If we're not on a boundary of the page size, so if we're not 4096 or 2 times 4096 or 3 times 4096, some multiple of 4096, 4K, if we're not on a 4K boundary, it's going to round up. And using this little bit of bit math that's defined here, it does that. If you kind of want to figure that out, I'm not going to explain it now because it's just going to take too much time, but copy it out, put it into a C file or whatever programming language you want to experiment with and play around with it. And the mechanism, if you sit down and you work out what's going on at the bit level by converting all your numbers into ones and zeros, you'll see that this is actually a really elegant way to round something up to a particular boundary, and it will only work in certain conditions, so you'll also be able to see that as well. But in this case, we're going to be going up to a 4K boundary. That's the point of that. So what's this whole thing about 4K? Because we've seen it a whole bunch of times now, right? We've seen the idea of this 4K in the stack and in other places. Well, in operating systems, you have something called virtual memory. Now, virtual memory is the idea that you have physical memory, right? We know that, for example, the kernel starts at this address. This is a physical address, right? This is an address on the machine that like it refers to something. A virtual address is something where you first have to go through a translation step in order to get to the physical address. And the benefit of this, or the point of it, in fact, is that we can use this virtual memory system to have process isolation in user space programs, or it's one aspect of that at least. So the idea is that any given user process, to the user process, it appears that it has its own full computer, right? It's the only thing running. It has access to an entire memory space, but all of its memory addresses are translated to physical addresses through a process called, virtual memory address translation. And that happens with a whole mechanism that involves stuff on the CPU. It involves page tables in memory. But the point I want to get to here is that pages are kind of the unit of virtual memory. So, like, if I have a virtual memory address, the way that it kind of ends up working is through that translation process, it always translates to one 4K block. Now, not to make things too confusing, but it doesn't have to be 4K, right? That's a sort of machine-specific thing. And it just so happens that on many systems, so including this risc-v system, including many x86 systems, 4K is the standard page size. But on other systems like the new Apple Silicon, they actually have a 16K page size. So they have bigger pages there. But the idea is that when you're doing virtual memory, it's done in blocks. Those blocks are 4K each. And any address that you try to translate is always basically going to point to one of those blocks plus some offset within that block. So you can't give a process or anything. You can't actually give a process less memory than 4K. Like, that's the minimum. Of course, you can always build other mechanisms around that, but like that's the point, right? When in the system doing address translation, multiple processes, 4K is the sort of the minimum unit. So the kernel also works in units of 4K because that just makes everything easier with address translation, right? If you make sure that everything that you're allocating lines up on a 4K boundary, you can just perform this address translation way easier. I'm not even sure if it's possible to do it without kind of making sure everything lines up on a 4K boundary. Probably not. I haven't really gone through the process of thinking that through. So, in the end, what we have now is the start address rounded up to the nearest 4K block, right? So all the memory that happens before that, there's going to be this little block of memory between the end of the kernel and the rounded up thing that's just sort of dead memory to us. We're not going to use that. It doesn't get used for anything. That memory is lost to us. But it's going to be of a maximum of 4095 bytes, right? So it's not that much in the grand scheme of things in terms of our 128 megabytes. I mean, it's not insignificant, but it likely won't be the worst case. And then what we do is we iterate using a for loop. So for, we've already initialized our value, so we don't do it there, but we could have moved this p here. While p plus the page size, which is 4K, is less than the physical end address that we are dealing with, cast to a character pointer, because then we can actually compare them in an accurate way. P plus equals the page size. So what we're doing is we're looping through, and at every step of the loop we are incrementing our pointer by 4K. So we're jumping to the sort of the next page. And we end up calling this function called kfree. So this is a page allocator, right? And what we're actually doing now is setting up all of our free pages. Like when the system boots, all of the pages in the system should be free. We haven't allocated any memory yet. But the process of getting to like a big list of free pages, we actually do that by piggybacking on our page freeing process. So it's quite clever in a way, but we end up calling the same kfree function that we use when we're actually giving a page of memory back to the system. So we call kfree on this pointer. That brings us down to this function. Free the page of physical memory pointed at by the PA, the physical address, which normally should have been returned by a call to kalloc, right? So getting and freeing memory is a two-step process. First you get memory, you do that with kalloc, allocate some memory. That's similar to malloc, right? Memory alloc for the user space. This is kalloc, kernel allocation. And of course, it mentions here that the exception is when initializing the allocator ck in it above. Well, we have seen that, so we won't go back to it. But we can use this same mechanism. Okay, so what do we do here? In kfree, we first set up a pointer to a structure, one of these run structures. This is this linked list that that we have up top that's just basically pointing to the next run structure. So we've got a kind of working pointer to a run structure that we can work with. And first of all, there is this kind of invariant condition. So basically, if this condition is broken, then there's something wrong and we have to just crash the system. It should never happen. We check it. This is something that you could remove if you wanted to, like, if you were really sure, but in essence, you probably wouldn't. This is just what you would call an invariant. If this is broken, everything else is broken. Okay, so the first thing that gets checked is the physical address, is it a multiple of page size? That's what this is checking, right? If it's not a multiple of page size, that means that we haven't kind of aligned this pointer to a 4K boundary. That's not going to work for us, so we would crash at that point. Again, if our pointer, our physical address, if it happens to be an address that happens before the end of the kernel, so if it's like part of the kernel, the code, the data, anything like that, that's also invalid. We can't free something that's part of the kernel because that's not part of our free memory. So that would also be a crashing condition. And if the physical address is bigger than the amount of memory we have, well, of course we can't free that memory because that memory doesn't exist. So then we would panic. And in all of those conditions, we just panic with kfree. In actuality, of course, this kind of thing, this is a fun trade-off that you see throughout the code base here. In order to, in a kernel, you have a different mindset to when you're programming applications. In the kernel, everything is about resources and just being really careful about your resources. You never want to make any code path longer than it needs to be because any time that you're running in the kernel is time that you can't run people's processes in user space. And in the end, user space processes, that's the actual usefulness of a computer, right? If you're spinning away in the kernel doing stuff, you're wasting time essentially. So what you'll see is that all three of these conditions, they all just map into this single thing. And of course, another thing that you don't want to do is to just like use too much memory. It's sort of the same thing in a way, but you conceptually sort of don't want to spend too much time in the kernel. You don't want to give too much memory to the kernel either, because memory of the kernel is memory that you can't give to processes. So in both these cases, the way that this is actually constructed is just a single if statement checking these three conditions, and then a single panic. You might think it would be more useful to have a panic for each of these possible conditions with a specific message of what happened. But that's kind of a different mindset. The kernel is really trying to make sure, like, okay, this should never happen. And if it does happen, you know, kind of, you're probably not going to figure out what went wrong just from seeing that single message. So right or wrong, that's kind of the mindset that's going on here with this kind of code. Okay, so there's a bit of divergence, but what does the rest of this function doing? So we're trying to free this page. The first thing we do with the page is we fill it with junk to catch dangling refs. So what's happening here is we're using memset set memory. So set the memory starting at this physical address and for page size. So for the whole 4096 bytes, set everything to 1. Just set every byte to a 1. Is it byte by byte or is it integer by integer? Yeah, it looks like it's like in units of U32. So it wouldn't actually set every byte. It would set every uint32. Okay, but we're going to fill it with junk. And what does this mean, this dangling refs? Well, basically, user space programs, they're gonna fill memory with variables and things like that, and some of those variables are going to be pointers. So you're going to have things that point into memory. Now, if you free a page of memory, and somehow a user space program still has kind of like a pointer into that, but it's kind of been freed, well, there are. Basically, what's going to happen is you're going to read a value that's kind of stale or old. That's kind of like a use after free problem. If you get into a condition like that and you read back the value 1 instead of the thing that you were expecting to read, especially if you had like an array of items and you were just reading these ones, well, this is a way that you would be able to catch that as an issue. And this is especially relevant in the kernel itself, right? If you were trying to debug problems in the kernel, this would be a good way of just figuring out like, oh, it looks like I've already freed this page. Okay, so what do we do actually? So we've set the whole page to be 1. What we do now is we actually take that physical address, which points to the beginning of a page, and we cast it to a pointer to one of these run structures. So remember this structure run, it's this thing here. So this is a bit of a tricky thing, and we haven't actually, of course, we haven't done anything with the memory itself. We've just got we've got a pointer to something here, and we're saying like, okay, the thing that this points at, the area of memory is over here. So we're just like basically telling our C compiler, no, this random address, oh, it's definitely a run structure. No, it's a run structure. I've checked it, and I know for sure it's a run structure. Of course, it's not, right? It's just random memory, but we're sort of imposing the lens of it being a run structure now. And so what do? We acquire the lock and then we release it afterwards. So we're just making sure we don't collide with any other CPUs here. And we set the R next. So basically we're going into the memory, the physical memory of this system now. We're going and writing the very first like 32 bytes, the 32 bits of it. We're writing it to be the address of, I guess this would be 8 bytes since it's a pointer. in a 64-bit system. We're writing the first 8 bytes to whatever our currently pointing free list is. So remember, we've got this kmem, and we've again got a pointer to a run struct here. So in the beginning, when we first boot the system up, this is going to be pointing to null. It's going to be a null pointer. So what we do is we set the pointer of this thing to be whatever the last one was. Then we say that our new free list is this random run structure, this pointer to a run structure, and then we release. Now, this probably doesn't make a whole lot of sense to you. This is a kind of piece of code that I think is really tricky to understand. Even if you're like familiar with C, I think that reading this kind of code can be tricky. So let's actually look at a diagram to make this easier. So what I've done here is I've kind of diagrammed out the memory of the system. So down here is the kind of the very bottom of memory. This is where the kernel code goes. Then we've got our kind of constant data. We've got our kernel RAM and our variables. And then kind of after all of that stuff, that's where our end begins, right? That's the end of all the kernel stuff. And then everything after that until the end of memory is just made up of these 4K pages. And I guess one thing that I should have drawn in this, in fact, is that this could be kind of not aligned properly. So maybe I should kind of put something in here just to show that this sort of isn't aligned necessarily. All right, so everything from this point onwards is 4 kilobyte pages. There's tons of them. There's going to be a lot of them in the system at that point. And what are we doing? So this just imagine that we just tried to free this very first page of memory, right? So we got our address, we rounded it up to the nearest 4 kilobyte boundary, and now we're going to try and free this page. So what happens? Well, first we check all of our conditions, right? We check that we're not like, we're properly aligned, that we're not like down here, that we're not beyond the physical top. So okay, all of those are good. Then we're going to set every value inside this to 1 so that we can kind of debug if something goes wrong. Then we acquire our lock, so we block any other CPUs from doing anything with the memory at the same time, and we set the next of our free list. Sorry, let's make sure we do this in the right order. So we set the pointer, this new pointer that we've got, we set it to be equal to our old free list. Okay, so what's that going to look like? Well, this is our kind of our free list. So our old free list is pointing here. So that's going to maybe look something like this. We end up kind of writing down that we're pointing down here. And then we set our free list to this page. So that's what's happened here. So now, and if we kind of zoom in on this, and I'm going to try and make something on the fly here, which is maybe not the best idea. If we kind of think about like just like this page as being, you know, a series of as things in memory. Well, in the beginning, we've like these are 32 bits at a time, so we've kind of set everything to 1 in the beginning. But then what we're actually doing at some point is we're saying that like the beginning of this, the first we're casting this memory address that points to this page. We're casting it to a run structure. So the run structure has a next. So the very first thing in here is now the next, and we're pointing it at our old free list. So this now becomes a null pointer. Right? This is kind of like this is kind of like a representation of what any of these 4K pages looks like. Okay, so like what we've done is we've pointed down here to null. That's the old free list, and we're saying our free list, and this is going to be a pointer that lives somewhere in here, right? In this part of the code, our free list just points at this, the new page. That's the next free page. So we freed one page. If we were then going to allocate a page, we've actually got one to give now. We can give this page. So like that's it. That's how this is going to work. Let's imagine we freed another page, right? So we've got the next page along. Let's let's move that up there a little bit so we've got like a new page to play with. So this is the next page, right? We started down here. We're going to add 4K, so we're now going to be here. I'm going to free this page. So what do? We set everything to 1 again, of course. So this is our new page. Set everything to 1. Then we take the pointer here and we're going to kind of point it at the previous free list. So what's that? That's going to be basically pointing to this area of memory. So we're kind of pointing down to the previous page. And then we take our free list and we point it here at this page. And of course what that means is that this one is kind of going to be like the address of this is going to be page roundup end, right? That's the address that's in the free list now, right? We're pointing, sorry, that's the address that we put in our next, like whatever the next page that we could give. So this is the first page we can give. This is the next page that we can give if this one gets freed. And then of course we're just going to continue this process. So let's get rid of that. Let's actually put in just like a couple more pages and then we can see the final structure on the fly drawing here. So we're just going to end up essentially disconnect that, take this. So we end up in a structure that looks kind of like this, with each page kind of pointing back at the next one, and then something like this. So the free list is going to start at the very end of memory, and that's kind of an interesting thing. Like it's a fun way of building a linked list. I think people you naturally imagine that when you're building a linked list, that kind of you start in the beginning and you point to the next thing and the next thing and the next thing. And the way that this actually builds it is that it kind of shifts things in from the bottom. So but by the end, you're actually pointing to the last item in the list, sort of conceptually speaking. It's the last item you dealt with, it's the first item you point to. So we end up like, if we're going to allocate a page of memory now, we're allocating from like sort of the very end of RAM. So that's where we would allocate, and then kind of the next page we would give would be this one and this one and this one and this one, and eventually we've got no pages left to give, we just got a null pointer. So that's how this works. I hope that this diagram has kind of made it a bit clear. It's a bit tricky, I think. And what really surprised me about this when I read through the code is that I imagined that in a kernel you would have sort of some structure somewhere that would somehow keep track of all of the free pages. So you would actually have just a piece of memory that was kind of a table, and it said, yeah, okay, this page is free, this page is not free. Maybe you would have two tables. But in fact, that's kind of not what happens. The memory itself is the data structure. That's kind of like, I think that's kind of a mind-blown moment. It was for me, like that we actually use that memory itself as the data structure that keeps track of which pages are free. This is kind of the beauty of C and having things like pointers, is that you can do this. You can just say, that random memory address over there, yeah, that's a linked list node. Actually, it's sort of like a 4 kilobyte page, but actually it's just a random memory address. We can say whatever it is. So no, it's a linked list node. Its first element says where the next thing is. And if we kind of follow those through, now all of a sudden, you have tracked all of your physical memory that you have to give away, and you haven't had to use any memory to store that. It's kind of mind-blowing because all that memory is free, right? It's not being used for anything. And the minute that you want to use it for something useful, you no longer have to use it to keep track of what's free, because you only ever keep track of what's free. You don't keep track of what's being allocated. I hope this makes some sense. It is a tricky concept, so if it doesn't completely click, then maybe try and download the code and step through it in the debugger, kind of try to write down physically what's going on, like what would the address be at this point. Okay, round it up, kind of go through these steps and see how it's working out. It's really eye-opening. I think it's a really, really very clever mechanism, and it's not the only mechanism, right? This is certainly not the mechanism that's used in Linux or anything like that. There are different algorithms that you can use for the same thing of kind of allocating memory within the kernel, but this is a very elegant way of doing it. I think it's very beautiful. So how does allocation look? We might as well talk about the full picture here. So how does memory allocation itself work? So here in kalloc, we allocate one 4 kilobyte page of physical memory. It returns a pointer that the kernel can use. It returns 0 if memory cannot be allocated. So why could memory not be allocated? Well, because there wasn't any, right? That would be the thing. So basically we're returning a null pointer in that case. All right, so what do? We keep track of a local run structure. We acquire the lock. We basically say that that's equal to whatever the free list is at the moment. Keep in mind again that our free list is just pointing at whatever our currently most free page is. So basically, if we got something that wasn't 0, i.e. Our free list wasn't down here pointing at null, it was pointing at like one of these valid pages in between. If we have that situation, then great. What we can say is that our free list is whatever the next one is. So let's have a look at that. What we're basically doing is we're sort of keeping track of what this one is. That's the one we're going to give away. And then we say, okay, the free list, now the free list is pointing at this one. So we've got this page, it's kind of ours to give away now, and that's what we would give away. And we don't have to keep track of it, right? It's just like a page that's free. So that is how that works. And then we release the lock. So it's a very simple mechanism, right? Just give the first thing you have available. And basically, if we do one more check down here, like if we got something, like if there is a page to be looked at, well, now we're going to set all of that data that was in there. And remember, everything is kind of like, we set it all to 1 before when we freed it. Now we're setting it to a new value. We're setting it to 5. So we're filling it with junk, but we're filling it with a different kind of junk to if it was a free page. And that's kind of also a debugging thing, right? It's very quick and easy to see when you're examining memory if something is filled with a 1 or if it's filled with a 5. And in the end, we just return what we got, that struct run pointer. We just convert it back to a void pointer and return that. So that's it. There's no special case to check if we didn't get memory because the free memory just points at a null pointer in the end. This is the entire memory allocation process. Really clever, if you ask me. Really, really clever. And what we'll see is that if we just take one peek into kind of the next function down, so we looked at kinit, we've now looked at the entire allocation process. If we look at the next thing here, when we init, and we follow a couple of these functions through, you'll see that one of the first things we do inside this function is that we allocate a page so that we can start using dynamic memory, right? So that's it. It immediately starts being used. We're going to look into that in the next episode. Yeah, for me, this has been a really fun one. I think it's a really beautiful mechanism, as I've already mentioned. I'm really curious as to what you think of it. Like, let me know in the comments if this made sense and if you kind of have any questions about it, and like if you would do it differently or if you have any other ideas. I'm really curious to see what you make of it. I've really been enjoying all the comments that have been coming in from people who have all different kinds of backgrounds. People who are doing web development but are finding this interesting. People who worked on Unix, in the 70s and 80s and are kind of being able to come and look back at this. It's great. So please keep letting me know what you think of it. If you have any interesting observations or anything like that or questions, I really welcome them. I really hope that you'll join me in the next installment of this series, where in all likelihood we'll look at the virtual memory system. Alright, thanks for watching. I'll see you next time.